Establishing a permanent human presence on the moon has moved beyond the realm of science fiction. Right now, inside cleanrooms across the country, engineers are assembling the actual physical hardware that will make it possible. We are attempting to build a habitat 238,000 miles away in an environment where temperatures swing from -334 to over 130 degrees. Because of physics, a single launch cannot deliver an entire moon base. The mass requirements far exceed our largest rockets. NASA's solution is a decentralized assembly line. During Phase 1, the agency will use over 20 distinct commercial lunar landings to incrementally deliver parts, technology, and science to the surface. This strategy treats the moon as an active construction site. Success depends on maintaining a continuous, reliable supply chain to transport materials across the lunar vacuum. Before heavy construction can begin, initial payloads must scout the terrain. These robotic precursors map hazards and identify zones free of Earth's radio interference to ensure the site is viable for long-term operations. Firefly Aerospace's upcoming Blue Ghost 2 mission will head to the far side of the moon to perform this scouting work. It will deploy the LuSEE-Night radio telescope and test early mobility rovers in a region shielded from Earth's electronic noise. At Intuitive Machines headquarters, the IM-3 Nova C lander is already built. This flight hardware is currently entering final testing before its mission to the Reiner Gamma magnetic anomaly. These companies are retaining the engineering teams from their first flights to keep knowledge in-house. This allows them to rapidly refine their spacecraft software and landing algorithms based on direct data from previous attempts. Proving we can safely and repeatedly land this hardware is a prerequisite for construction. These reconnaissance missions establish the flight reliability needed before we attempt to deliver heavier cargo. The next phase of the blueprint involves moving larger components. We must deliver heavy construction equipment and infrastructure-class payloads to the hazardous, uneven terrain of the lunar South Pole. Voyager's Griffin 1 lander is designed for this scale. It is tasked with carrying the Astrolab FLIP rover, which currently stands as the largest commercial payload targeted for a South Pole delivery. As this diagram illustrates, carrying bulky cargo creates significant stability issues. Engineers must map the spacecraft's exact center of gravity and moment of inertia to ensure it remains stable during the descent to the lunar surface. Griffin 1 is currently at NASA's Jet Propulsion Laboratory for environmental testing. These tests verify the lander's physical mass properties against digital models, identifying any discrepancies before the vehicle leaves Earth. Successfully delivering these larger rovers and equipment sets the stage for advanced operations. It demonstrates the logistical chain can support the hardware required for a sustained lunar presence. The ultimate requirement for the lunar blueprint is the deployment of human-scale technology. We must ensure life support systems survive the extreme environmental conditions of the moon. Blue Origin is utilizing the heavy lift capacity of the New Glenn rocket to test these systems. Their Blue Moon Mark 1 lander will prove out precision cargo offloading and liquid hydrogen systems in preparation for upcoming Artemis human landings. Electronics and life support systems face a constant threat from the South Pole's thermal environment. The intense swings between extreme cold and heat can easily destroy sensitive hardware if it is not properly hardened. NASA and Northrop Grumman are addressing this challenge by repurposing proven systems. They are adapting the power, avionics, and communication hardware originally developed for the Gateway's Halo module to function on the lunar surface. Long-term lunar survival relies on the pragmatic reuse of space-tested hardware. Adapting existing, flight-proven systems allows us to build reliable infrastructure capable of enduring the moon's brutal thermal cycles. The 1960s space race relied on a single launch paradigm, using the massive Saturn V to reach the surface for short-duration missions. The modern blueprint replaces that bespoke approach with a multi-company assembly line. This strategy is built on iterative mass production. By designing spacecraft for high-frequency repetition, commercial partners can move from individual experiments to a continuous delivery cycle. This production model is already visible. Blue Origin is manufacturing 4 landers simultaneously, and Intuitive Machines has scheduled deliveries extending through IM-6, allowing teams to apply lessons from one mission to the next in real time. A repeatable manufacturing cadence naturally drives down launch costs. As the volume of flights increases, mission reliability grows, making the transport of cargo to the moon a routine operation. NASA's 20-mission blueprint establishes a permanent logistical highway to the moon. By coordinating these incremental deliveries, the agency is building the physical foundation for a sustained human presence in deep space.